hopefully a few more folks will trickle in. If not, then we will get going. So 2 anecdotes to share with you over the weekend. Does anyone else watch Grey's Anatomy still? Yes. Okay, did you watch this week's? Yes, you're laughing. It was really pretty funny. So I have an anecdote to share with you over my weekend. So my child, of course, loves Paw Patrol, which is a cartoon about dogs that save the world, because all of the humans in the cartoon are just ridiculous. And the dogs get bones. They get, like, basically dog treats. And he's like, well, I want a dog bone. Like, people don't eat dog bone. And his dad's like, well, let's see if we can find some. And they went to the grocery store, and I kid you not, they came back with Scooby snacks, which are dog-shaped graham crackers. So I always thought Scooby snacks was a euphemism for what one ate on, like, 420, perhaps. Turns out, no, it's a thing. So if any of you have children who ask for Scooby snacks, don't call Child Protective Services. Go to the pantry and see if they have any graham crackers. Yeah, so yeah, it was really quite funny. And the other thing, sadly, is that I may be less animated than usual because the only cold soda in my fridge was this one. My Diet Dew was all gone, which is very, very sad. It reminded me of the time that I gave a workshop at Brigham Young University. I was invited there by someone I was a postdoc with, and it was a 4-day workshop, and so I had my coffee at the hotel the morning of the first day, and then at lunch, all there was lemonade and fruit punch. And I'm like, how the hell am I supposed to survive on that? So the next day, I asked the person who was driving me to stop at a convenience store, and I grabbed 2 emergency 20 ounces of real Mountain Dew to power me through the day, and I did so for the next 3 days. Yes, when it's an 8-hour workshop, I go for the real stuff. But today, it's just placebo, so we'll see if you can tell the difference. So there's no homework out right now. It's still being built. It is going to be a story about cortisol and stress, I've decided. Since no one cared, the only person who seemed to care was you. You get what you want. You get a homework. And I think, Lindsay, you do stuff with cortisol too, right, and spit? So is it more correct to say that they spit in a cotton ball or they put the cotton ball in their mouth? A swab. Is it like a Q-tip or like a cotton ball? Because I'm going for authenticity with the story here. That's okay. I want, like, do they spit in the cotton ball? Do they chew on it? Okay, so if you were going to swab, say, a fellow grad student, what would you do with them? They would drill into the container. Okay, so that's what we're going to do. Probably, hopefully done by Wednesday. The previous homework, not everyone is finished with yet, so we'll delay talking about that, but I'm happy to answer individual questions if you have it. Otherwise, we can go back to talking about 3-level models, right? Why not? You've come this far. The good news is that there really are no new concepts at this point. It's just everything you've learned at the same time, other than link functions. No link functions in these stories. So let's review, shall we? Talking about interclass correlations and slopes and stuff like that. So 3 levels. The idea is if we have, say, an example of time within person within group, we start out with all the variation being attributed to what we think is level 1. First thing we had done is split what is person level 2 versus level 1 still. Interclass correlation at level 2 then tells us how much of the total variation is level 2. It is also the expected correlation of times from the same person. We would then do a second partition of that level 2 variance. How much is actually level 3? How much of what we're calling person is actually group instead? That gives us a level 3 interclass correlation, which is the expected correlation of persons from the same group. And so when we compute these things, notice that the level 3 interclass correlation does not include level 1 in the formula. It's of the variation that's 2 and higher, how much is 3? That's why it becomes the correlation of persons from the same group because it is ignoring occasion at this point. So you can think of it as a partition of just the cross-sectional variation in this type of story. When we did, let's see, we're going to go back to that one. When we did slopes, we did the same idea. The person slope originally comes out of the level 1 residual variance, which is, why are you off your line today? Well, maybe you need your own slope. But then we can take that level 2 slope variation and see how much of it is level 3. So how much of the change over time, individual differences in change, is common to the group that people are from and not just the people. And it is technically possible to have slope variation for time that is all persons or all groups or some combination thereof. It's more likely in this kind of design to have it be some of both, but mostly person, I would say. We'll see another type of design later on that is a little bit different in that regard. So then we have a model that would look like this. So is beta 0 a parameter or a placeholder? Make this multiple choice. Placeholder is, let's see, these thingies are delta. Are these parameters or placeholders? Those are placeholders. That's the shift in the notation. That's a placeholder for what happens at level 3. So the only parameters are the red things here. These are our fixed effects. In this case, this is the fixed intercept, and this is the fixed slope for time. And then the U's, the V's, and the E's are not parameters per se, but they represent parameters. The U's are the idea that we have person variances in the intercept and in the time slope. That's U0 and U1 respectively. The V's are the idea that we have group variation in the intercept and the time slope. And E is the idea that we have level 1 residual variation. So both the U's and the V's are random effects, but they're random effects at 2 different levels. So there would be a covariance among any U's at level 2. There would be a covariance among any V's at level 3, but not anything across level 2 and level 3. So we did some examples with twin stuff before, looking at partitioning of intercepts and slopes, as well as zygosity differences therein. So any questions about that example before we move on to predictors? Nope? Crystal clear? You got it? All right then. If folks are still chewing, maybe that's part of it. But you can nod. It's still polite to nod or shake your head with your mouth full, I think. So random slopes then. So we've looked at an instance in which a level 1 predictor, such as time, in a clustered longitudinal design, has level 2 random slopes and level 3 random slopes. So we would say that there's a level 2 variation across persons in the level 1 effect of time. We could also say there's level 3 variation across families in the level 1 effect of time. But in 3-level designs, level 2 predictors can also have random slopes over level 3. So more generally, any predictor can have a fixed effect at its level and a random effect at any level above it. So that's why level 1 things can have level 2 variation. Level 1 fixed effects can vary randomly over level 2 units. Level 1 fixed effects can vary randomly over level 3 units. Level 2 fixed effects can vary randomly over level 3 units also, but level 3 fixed effects cannot have random effects unless there's a level 4. So 3 is the top of the order here. The more random effects you add, the more likely your model is to break. So I would still, in contrast to others, encourage likelihood ratio tests to decide which terms are significant, and try not to include too many things that are borderline or non-significant, because that's more likely to lead to non-convergence. That's an area in which Bayesian estimation, MCMC, tends to be used as somehow solving that problem. It doesn't necessarily. It depends on the prior that you're using, and that's an active area of research. So Bayes doesn't necessarily fix non-convergence without making other problems in the process. So it's an active area of research, just to say. So let's talk about smooshing then. Any predictor that has variation at multiple levels of analysis is going to become multiple predictors. Same as before. So let's think about a context here of a clustered longitudinal design let's say that we collected stress education as well as our outcome of well-being. So to the extent that sometimes are more stressful than others, there is level 1 variance in stress, and that level 1 variance can have a level 1 effect. So you can have an effect of having more stress than usual on one's well-being relative to usual. To the extent that some people have more stress than other people, then stress has level 2 variance. And so being a person that has relatively more stress than other people can predict having different well-being than other people. But in a model where people are both people and groups, it's relative to the group. So level 2 is person relative to the group, so it's the effect of, say, having more stress than someone else in your family, versus level 3 being part of a family that tends to have more stress than other families. To the extent that there's variation across families in stress, that level 3 variation can predict level 3 well-being. So for any predictor that is measured under level 3, level 1 or level 2, you want to fit empty models to try and figure out at what level the predictor has variance, and then you have a choice to make in terms of how you put that variance in the model. So we had talked about, in the context of longitudinal data, person mean centering, in the context of clustered data, group mean centering. I'm going to generalize those to be either variable-based centering or constant-based centering. The idea that you are centering either at a variable or a constant, and what the resulting fixed effects then mean. So the same thing will hold in terms of a level 2 variable. To the extent that a level 2 variable has variance at level 3, that variance at level 3 can have a differential effect than the level 2 effect. So what if I have a level 1 predictor that has variance at all 3 levels? This is how I would carve that up into observed variables. So I would take my level 1 time-varying predictor and I would make 3 new variables out of it. At level 1, if I were using variable-based centering, it's the idea of taking out all of the upper levels of variance and isolating just the level 1 part. What is the effect of having more stress than usual? If I take out person mean stress, that removes all the level 2 and 3 variance, and so what's left at level 1 is purely the level 1 effect, so it becomes the total within person effect of having more stress than usual. If you leave it out, you're assuming it's 0, the same as any other predictor. Level 2 then, you're used to putting in the person mean minus some kind of constant. Here's the switch. Level 2 is also going to be centered at a variable, which is the level 3 mean. So in this story, it would be person mean stress minus family mean stress. And then a 0 means that you have an average amount of stress on average relative to your family. So we're talking about tendencies and to what extent your tendency to be a stressed out person is greater than someone else in your family or your group. So by isolating this variance of person mean minus family mean, it's purely level 2. That's the only effect it can have in the model is the within family effect. So it becomes the total level 2 effect of having more stress than other people in your family. Then at level 3 comes the constant, so that 0 means something. So level 3 in these models will always be centered at a constant, so that 0 means something. What constant that is doesn't really matter. And so I'm calling that between family stress, and that directly tests the effect of being from a family that tends to have more stress than other families. So I like this approach for anything involving longitudinal data, because then you have a very clear demarcation as to what each term means at each level and what it's supposed to do. So in terms of pseudo R-square, let's do a little reviewing here. If this level 1 time varying stress variable is purely level 1, which variance component is within person stress going to predict? Residual, yay, we got it. And you didn't even hesitate that much. Remember, it's better to be wrong than vague. Level 2 person. If within family stress is purely the difference between you and your family, which variance component is that going to predict? Level 2. Level 2, finish the sentence. Yeah, random intercept. Maybe I didn't need the do after all. I just needed some right answers, right? Said without hesitation. Last but not least, level 3. This is only family stuff. Therefore, it can only predict. Yeah, level 3 random intercept. You got it. That's why I like this. You carve it up yourself. You know what it means. You know what it should do. Multivariate models, which I swear we're going to get to at some point, maybe not until next week, but we'll get there. This is what essentially happens. This is the analog of what the model is trying to do in building circles, right? You start with everything in E, that's the analog of just your time-varying stress variable, and it separates out its variation into what is level 1 across time, level 2 across persons within families, and level 3 across families. So what a level 3 random intercept means conceptually is family mean differences in an outcome. That's the same thing that its family mean stress is trying to do. What a level 2 random intercept means is variation of a person within your group in the outcome. That's what this level 2 predictor is trying to do. And last but not least, level 1 residual is within persons over time. That's exactly what this within person variable is trying to do. So I like this approach because of the symmetry on the X side and the Y side. It lends itself directly to multivariate models because that's what they are doing without you having to do it by brute force. It carves it up for you anytime you have a predictor that you're treating as another outcome. So this is what the equation would look like for something like that. So I have here, this would be a random linear time model with main effects of stress at each level using variable-based centering. So just to remind you, TIJ is time with an individual within group spelled wrong, called group or family, take your pick. Level 1 has 3 beta placeholders. Beta 0 IJ is how each person gets their intercept. Beta 1 IJ is how the linear effect of time varies over persons. It's how each person gets their own time slope. And beta 2 IJ is how each person gets their own within-person effect of stress. So this is displaying the centering here. So each of those betas then is how each person gets something. It starts off with the level 3 placeholder for how the group that person belongs to gets something, plus whatever fixed effects at level 2 and random effects at level 2. So right off the bat here, we're picking up a gamma O1 placeholder for the person level effect of stress, which is person stress minus family mean. And here's my person random deviation, U0. We have a random slope for time, that's U1 here, as well as the placeholder for how the level 3 effect of time is going to get built. Beta 2 is how each person gets their own within-person stress effect. That's a placeholder for what's going to happen at level 3 plus. I have in parentheses here. U2 meaning that it would be optional and testable whether or not we need it. What would U2 be in the context of this story? Person variation in the effect of stress, which one? Level 2 person variation in the effect of level 1 stress, which is within person stress, yes. So the extent to which some people are more reactive to more stress than usual, that would be U2 here. It has to be level 1 stress because this is level 2. You can't have a level 2 random effect over level 2 units. So we have, this is the level 2 variance, the idea of a level 2 variance in the level 1 effect of stress. I didn't do that, I swear. Creepy. Okay. So you know how there's 1, 2, 3, 4 delta placeholders here? Guess how many level 3 equations that makes? Feel free to count. 4, yeah. So delta OOJ is how each family gets their own intercept. We start off with the fixed intercept. Hey, wake up. Gamma OOO. So that is the average intercept across families for families that have 0 values on any family level predictors, such as family mean stress. So family mean stress is a fixed effect at level 3. In terms of the subscripts, the level 3 subscript gets a 1 here because it is the first predictor of the intercept. VOOJ is my family level 3 intercept that we had before. The next one then is delta O1. That's how each family gets its own effect of person stress. So if you wanted to see if the effect of being a relatively stressed out person relative to your family varied as a function of some family characteristic, those fixed effects would go in this line to become cross-level interactions between level 2 and level 3. I have VO1J in parentheses here. Here, I'll walk you through this one. Is V a fixed thing or a random thing? Random thing. Is V a level 2 thing or a level 3 thing? 3. So we know that it is level 3 random variation in. What is it variation in? What the hell does delta O1 mean again? Person mean stress minus family mean stress. So it's between family variation in the effect of being a more stressed out person than other people in your family. Perhaps not very likely, but theoretically possible. More generally, any level 2 fixed effect can be random over level 3. So that's why I have this in parentheses here to convey that that could be there if you wanted it to. Gamma 1 OJ is a whole separate thing, not to be confused with gamma O1J, 1OJ. And this is why I screwed these things up forever and ever and started writing out next to them what each of them meant, because this is almost impossible to wade through otherwise. So that's why I have my little Cliff's note on the side here to keep my memory going. So gamma 1OJ is how each family gets their own linear slope for time. So that's where we pick up gamma 100. That's my fixed time slope. If I had any family level predictors that I wanted to say, are there family reasons why this time slope differs, those cross-level interactions would go in this line. So family predictors interacting with time would go here. V1OJ is my family level linear time slope variance, so family level differences in change over time. And then last but not least, gamma 2OJ is right here. Here's my fixed effect, 200. So this is the fixed effect of, within person stress. Gamma 200 is the within person stress fixed effect. I have the V in parentheses because you could have family level variation in the extent to which having more stress than usual affects your outcome. So this is a specific example, but I want you to hang on to the big picture here. If I have a level 1 predictor, to the extent that it has level 2 variation in it, that level 2 variation plays a role as a predictor. That level 2 fixed effect could be random over 3. To the extent that I have a level 1 predictor that also has level 3 variation, that level 3 variation plays a role as a fixed effect, can't have a random effect. Any fixed effect at level 2 can vary over 3. Any fixed effect at 1 can vary over 3 and 2. 2 and 3, excuse me. I'm trying to go up and talk at the same time. It's not working for me. So that's variable-based centering. Questions or things you want to hear again about that? So level 1 is centered relative to 2, the mean at 2. The mean at level 2 is centered relative to the mean at level 3. The mean at level 3 is centered relative to a constant. And that could be like the mean of the means if you want, so that 0 means something with respect to your intercept. Yes. So to the extent that a level 1 predictor has random variation across level 2 and 3, you can calculate an interclass correlation for that random variation to see how much of it is really 3 instead of 2. So if we have an intercept, for instance, and we have a random intercept that varies over level 2 and level 3, that's what creates a 3-level model in the first place. 3 variation over 3 plus 2 gives us the interclass correlation for the intercept specifically. So this really is the same thing as what I was calling a level 3 interclass correlation, just without using that terminology because there was no other kind. So the interclass correlation for the intercept is a level 3 interclass correlation, but more specifically, it's a level 3 interclass correlation for the intercept. So if we go back to this picture, it's this initial demarcation of how much of my person intercept is group intercept, a level 3 intercept ICC. Then we can do the same thing for any level 1 slope that has level 2 variation across, or random variation across level 2 units and level 3 units time. Same idea, but now with the slopes instead. So the top here is level 3 time slope variance divided by level 3 time slope variance plus level 2 time slope variance. So it's like, of all the reasons for change, how much of them are due to group relative to person? So it's an interclass correlation of slopes specifically. And it is only possible to calculate that if you have a level 1 predictor that has a random slope both at level 2 and level 3, and all other random slopes are parallel in structure like that across the model. So I have an example of a non-parallel structure that wouldn't make sense here. Let's say that I also had a quadratic time term in the model, and I only had random quadratic time variance across level 2. It wasn't significant at level 3, or it blew up when I tried it. In that case, even though there's a linear slope random effect at both 2 and 3, I would argue it doesn't make sense to compute an interclass correlation for it because what it means is not the same. Given the random quadratic at level 2, this linear slope variance is specific to time 0, but without the random quadratic at level 3, this linear slope variance is not specific. It's across time. So they don't mean the same thing, and to me, carving them up into 3 versus 2 doesn't make sense if the term you're carving doesn't mean the same thing at 3 versus 2. So you can do this type of description anytime that you have a level 1 term that varies over both level 2 and level 3 units. Does that help? It's a level 3 interclass correlation for the time slope specifically. It is only possible to the extent that there is time slope variation across both level 2 and level 3 simultaneously. You got to have all the numbers that go into the equation in order for it to work. And you can think of these as effect sizes for the decision to model a slope at both level 3 and level 2. This number should be sizable. The significance test for it is a likelihood ratio test, same as usual, for adding it to 3 after it's already at 2.
So would there be a level 1?
No. Nope. There's a level 2 ICC that would include, let me go back. The level 2 ICC is the one that you know that includes all the variances in the denominator. And it includes 2 and higher. So this level 2 ICC is a proportion, how much of the variance is cross-sectional, It also tells you the expected correlation of occasions from the same person. And because people are nested in groups, it's occasions from the same person and group as together. You can't split them apart. It loses its interpretation once there are random slopes in the model, because then it becomes conditional on when time 0 is, and that's why I switched sort of the definition to intercept specifically, as opposed to just, technically these are intercepts, so it might be a semantic distinction, but yeah, this level 2 ICC is not something you would continue to talk about once there's other random effects in the model, because I don't think it's not specific enough, and it also changes to the extent that there are slope variances. So level 3 then, ICC, is carving up level 2 and level 3 things, ignoring level 1 residual. Does that help you? Okay. Can I help anyone else? No? All right. So instead of variable-based centering, the other way that one could go about including these 3 variables in the model, if you have a level 1 predictor that has variance at all 3 levels, is constant-based centering, or grand mean centering. And the difference lies in how you define the lower level effects. Instead of centering at the next level's mean, center at a constant. It can be the same constant or a different one, doesn't really matter. The idea, though, is that you're not carving up the variance into its respective levels. You're going to let the model do that as a statistical control once they're all in there, and it's going to create contextual effects. So in this specification, level 1 has all the level 1, 2, and 3 variants in it. Once we control for the level 2 variance and the level 3, it becomes purely level 1. Person, though, is the extra part that level 1, above what level 1 has, and so it becomes a contextual effect, and the same thing happens at level 3. It becomes a contextual effect. So technically speaking, if you wanted to test whether or not smooshing was acceptable across all 3 levels, setting up the model this way tells you that directly. The contextual effects give you the difference in what to expect across levels. So level 1's effect plus level 2 contextual gives you the level 2 effect. Level 1 plus level 2 contextual plus level 3 contextual gives you the level 3 effect. And there are very few instances in which I would recommend going about it this way because of the challenges in interpretation. But the equation that I just showed you would look exactly the same. The difference is how the variables are formed, and thus what the higher order fixed effects would mean. The other trick is in terms of what it means to omit the variables. Whenever you're doing variable-based centering and you leave something out, you're assuming it's 0 at that level, same as usual. If you're doing constant-based centering, leaving stuff out is akin to smooshing. So let's say that I have constant-based centering where I would have a level 3 contextual effect, a level 2 contextual effect, and a level 1. If I take out the level 3, I've smushed level 2 and level 3 together, but they're not smushed into 1 until I remove level 2, in which case level 2 and 3 are all smushed into 1. I don't like the constant-based centering because when you leave stuff out, you're not assuming 0. You're assuming that what you left out is exactly the same as what the effect would be at a lower level, which is more problematic. And then interactions, even more fun. We'll delay that for just a minute. Okay. So, level 1 effects. Level 1 predictors can have random effects over 2, yes or no? Yes. Level 1 fixed effects can have random effects over 3, yes or no? Yes. Level 2 fixed effects can have random effects over 1, yes or no? No. Level 3 fixed effects can have random effects over 2, yes or no? Level 3 fixed effects can have random effects over 3, yes or no? 3 over 3? Nope, not random over itself ever. Finally, level 2 fixed effects can have random effects over 3, yes or no? Yeah! We got it. Do you want to see another example? So the example that I built for you is brand new this year. I spent a long time on it, and I'm very proud of it, and such that it was, I'm actually going to try and turn it into a couple papers. So you will have seen it first. I'm looking at example 8B here. So this type of design goes by a lot of different names. I know it as intensive longitudinal. Ecological momentary assessment is another buzzword. Can you think of others that this goes by? When you make people fill out a lot of surveys a whole lot of times? No? Okay, those are the two terms that I know of. But these are real data that I borrowed from Chris Cushing. And it was part of a pilot study he collected when he was still at Oklahoma State University. We have 25 adolescents who completed surveys 4 times a day. They got to pick what time of day the surveys were, but they were within certain ranges. They were supposed to be before they went to school, over lunch, after school, and before they went to bed. They did self-report surveys on smartphones about their mood and energy levels, and they did this for 20 days in a row. So after a little bit of cleaning because of data entry errors or missing data problems or things, I ended up with a total of 976 observations. So what we're looking at here then is going to be how self-reported fatigue varies throughout the day, how negative affect relates to fatigue, and how variation in sleep moderates those associations. So I went into this thinking that, guess what? If you're more tired, maybe you're more grumpy. Or maybe you're more grumpy makes you more tired. I'm not sure. That was my driving hypothesis, and I wanted to see if getting more sleep would help lessen the impact of grumpiness on fatigue. That's my thing here. Because I'm looking at last night's sleep as a predictor of things, and because of issues about first-day reactivity, typically people find in these studies that people are reactive the first day to the measurement process. Their scores look a lot different than on subsequent days. So I carved this up into days 3 through 20, and these are the variables that we're going to look at here. So we have hours of sleep, which was collected by some kind of like Fitbit kind of thing that did it automatically, so it's not self-report. That is going to be measured each day. So I'm looking at the night before. We're going to treat that as a moderator. Fatigue is my outcome. It was measured 4 times a day, but time is unbalanced. So even though I may have like occasion 1, 2, 3, 4 in the data set, when those occasions actually were is variable across not only days, but persons. So we can look at a lot more information about changes in fatigue across the day by sort of stringing together all of the observations. So we have 3 items measuring fatigue on a 1 to 5 Likert scale. Negative affect was measured at the same 4 times using 5 items. We're going to treat that as a predictor. And then the time of day itself, we're going to use that in 2 different ways. One is just to track changes throughout the day in fatigue, but then also look at to what extent person choices and when they completed these things, like whether or not they woke up early or late, is a moderator of the effects of time of day. So it's a fairly straightforward example in the sense of I'm looking at how sleep moderates the association between fatigue and negative affect throughout the day. That's what I'm looking at. To do that, though, took, 14 pages or something. And that's not even with all my usual stuff here. So here's the data set up here. I'll explain these variables as I need them. One thing I needed to do right away, though, was create one combined variable that is for person and day. Here's a trick to do that, by the way, that's very easy. I had person ID in one column, and I had day from 1 to 20 in another column. If you add person ID to day, that won't work. But if you divide day by 100, then it becomes like 100.1, 100.2, 100.3, and you can use the decimals to your advantage that way. So it's an easy way to take 2 ID variables and merge them together. Move one to be the right of the decimal. There's also a time function. I have hours since midnight. So there's a time function that SAS understands what time of day is, and so I divided that by the number of, I'm going to go with minutes. No, this is seconds. Seconds in an hour to create hours since midnight. SAS also has a function for day of the week. So it knows what day of the week it was if you give it a date, and it will spit that back at you. And so I have a code here that we'll use for that. So I'm sorting. And the first thing that I'm going to do here is get day level means and person level means. So I'm going to have to carve up my negative affect and my time variables into their respective levels. I need the means to do that. So the first step here is to carve up my variables of hours of sleep, negative affect, and hours since midnight and get their day level means. So I'm doing this by person ID day, and day. And yes, these are redundant, but I keep them all in there so that they're all within that data set so that I can do descriptive analyses on that level 2 data set. So I'm creating a new data set called day means that is the mean hours of sleep. So that's just an easy way to collapse across the identical information for the 4 observations. The mean negative affect for that day, and the mean hours since midnight of their observations. So I'm controlling eventually for the fact that people choose when they complete these surveys. I'm creating then these 3 new variables. Here is lagged sleep, this little step right here. Proc expand by person ID. Day keeps track of which is which, and so I'm converting sleep into a data set in which it's lagged down 1 row. So last night's sleep is on the same row as today's fatigue and negative affect. Proc expand, when you use these ID variables, understands not to lag it into the next person's data, so you don't have to worry about that. I then took that new data set that has lagged sleep, and I did means by person and created a new data set called person means. So I have person mean day sleep, person mean day negative affect, and person mean days since midnight, or time since midnight. So the order of operations matters whenever you have unbalanced data. I have my level 1 observations, and I compute my level 2 mean. I then take those level 2 means and compute my level 3 means. That ensures that each day gets equal weight, even if not the same number of observations went into each day. Okay, does that make sense so far? So we're merging the day means into person means into the day means, creating my level 2 and 3 variables. So level 3 sleep, I'm using variable-based centered sleep. So level 3 sleep is person sleep, so that's their mean hours of sleep across the days that they gave me, minus 7, because 7 was the average for the sample in terms of the number of hours of sleep that these kids got. Level 2 sleep then is their night before sleep minus their mean. So level 2 becomes, hey, did you sleep less last night than usual? Regardless of what usual is captured by this person sleep variable over here that's at level 3. Did the same thing for negative affect. So I have level 3 NA for level 3 negative affect is person mean negative affect minus 10, which was near the mean of the scale. So that distinguishes people who tend to be grumpier than other people. That's a level 3 person level variable in this study. Level 2 then is day relative to person. So are you grumpier than usual today? That's level 2 negative affect. And I'm switching for contextual effects because they're easier to interpret with respect to time to get my level 2 time variables. I didn't end up using this one, so that one we don't actually need. But I have level 3 time, which is person hours since midnight minus 15. That means I'm centering at 3 p.m. as their average time that they completed these studies. Last but not least, I take that level 2 and 3 data set and merge it back into level 1 to create my level 1 predictors. So level 1 negative affect is your current surveyed negative affect minus your day mean. So are you grumpier right now than you were the rest of the day? Level 1 time is how long it's been since midnight, centered at 3 p.m. So the intercept in this model is going to be from mid-afternoon in terms of when we're predicting fatigue. And then I also created this rounded time of day variable so that I can make pictures to try and discern what kind of trajectory fatigue takes across the days. Last but not least, this step right here, the where and miss function, this limits my analysis to only cases that have all of the information that I'm going to need. Otherwise, as you add predictors, it will drop the cases that don't have those predictors, and any -2 log likelihood tests will be messed up, as well as any pseudo R-squares will be messed up. So you can't have, like, say, the variance components from an empty model and then calculate their proportion reduction from a predictor model that has fewer cases. It doesn't match. So this step ensures that even before the variables go in the model, all of these models are based on the same 976 cases. And here are the means for the variables. So fatigue, negative affect, last day's sleep, and since midnight. So this is a 3-level design that is different than the one we looked at last week. Last week it was time within person within twin pair. This is occasion within day within person. So time is 2 different levels. It is both when you completed the survey within a day and which day it was, 3 to 20. And then people are level 3. Okay, with me so far? All right, so now we get to do the slide that I kept skipping, because I'm going to give you a different kind of interclass correlation that is more useful in a design like this. One of them I talked about in the book, and the other I just made up. So you heard it here first. ICC Level 2B, brand new thing. So we're starting out the same way. Once upon a time, there was an E. So this is, for instance, all of the variation in fatigue across occasions, across days, across people, one pile. First step is I'm splitting what is eventually going to be level 3 from what is level 1 and level 2 combined. So in intensive longitudinal data, people will automatically assume that there's variation between persons and within persons, right? That people need their own whatever, because that's usually the whole point of including more than one person in these designs. Otherwise, it would be a time series. So the idea that occasions from the same person will be more alike than occasions from different people, that's a duh. That's what this model gives us. So what's eventually going to be level 3 gets an intercept first. So we're differentiating what is between person from what is within persons, same as if it were a 2-level model. The next step then is to differentiate what we're calling within persons to be more specific. To the extent that occasions from the same day are more correlated, this model is inadequate. This model predicts the same correlation across all occasions from the same person, regardless of which day they were collected on. But if you feel really crappy one day, to the extent that that crappiness, it goes across all 4 observations for that day, right? But maybe you get some sleep and you feel better the next day, and the next 4 observations are better. That kind of day-specific phenomenon merits another level of the model. So we're going to take what was this combined level 1 and level 2 within person and split it into within and between days. So then we really do have a 3-level model, but I'm going about it in a way that makes more sense for the design. So ICC level 3B in this case is how much variation is level 3 out of the total. How much variation is cross-sectional out of the total, whereas the second split of the time part into within day and between day gives us ICC level 2B, which is the test of whether or not we need a 3-level model for these data or a 2-level. So a 2-level model would put all occasions into level 1 and people in level 2. It would ignore the fact that occasions are nested in days. Whether or not occasions need to be nested in days is tested by including a day-level random intercept in the middle, which is level 2. And the interclass correlation for that would be of what we used to call just level 1 within persons, how much of that is specific to the day? Do we need a level 2 in the middle to differentiate occasions from the same day or not? Empirical question. So here then would be what those indicate. And this, by the way, this version of ICC level 3, that's what status spits out, and that's what M+ spits out if you ask for a 3-level interclass correlation. It is not the kind that I taught you. It's this one. So in the book, I talk about ICC level 3B. This is the one that I had to invent for this type of design. So the moral of the story, don't ever just say the interclass correlation was 0.3. Right? Don't ever say that, because you've learned like 6 of them today alone, right? The interclass correlation of blah, 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 and maybe even give the formula, was this, indicating and then interpreting it. So let's look at how this plays out in our example here. So here's fatigue. Do you think that at some times a day you're more tired than others? What do you think? Yes, probably. Like right now, perhaps, just as an example. Are you more tired on some days than others? Do you think some people are just more effing tired than other people as a trait? Like poor grad students, just hypothetically, right? Yes. So we have a hypothesis here just from life that fatigue needs a 3-level model. So let's test it. So here is my 3-level empty means model. So level 1 is time, level 2 is going to be day, and level 3 is person. I am keeping the same levels and the same equation structure, even though level 2 doesn't technically exist right now. What I have, by the way, this is TDI for time within day within individual. You can make up whatever subscripts you want, and I think it makes more sense when the letters follow the design. Here's my level 2 intercept placeholder. So BODI is how each day gets its own intercept. Right now, there's nothing here but another placeholder, because there's no terms related to day in the model yet. How each day gets its own intercept happens at level 3 here. How each person gets its own intercept. This is my fixed intercept gamma 00. Here's my V for my random intercept across persons, and the only other variance is E here at level 1. So if we look at the variance structure of this model, I'm in REML because I only have 25 people. This is a 2-level model. So subject equals person means that everything that's within persons is relegated to level 1 residual. It makes no differentiation between occasions and days. It's all just level 1 pile. I am saving the fit of this model, InfoCrit, fit, and it's for the DV, and this is 2-level. So we have a lot of these we're going to do, which is why my naming system has to get a little more specific than usual. So here are my variance components. 6.7 is the variance in fatigue that is person level. So yes, indeed, some people are more effing tired than other people. And residual is 6.1. So if I compute an intraclass correlation the usual way of between over total, half of the variation in fatigue is systematic to the person, 52% more specifically. So yes, some people are more tired than others. In some occasions, you're more tired than others. So this model assumes that all fatigue occasions are equal, doesn't matter what day it is. So my effect size of whether or not person matters, whether there's any person dependency, is this intraclass correlation of 0.5 right here. Here is my likelihood ratio test that would compare this model against an E-only single-level model. The difference in -2 log likelihood is 429, so yes, this 50% is not 0. Okay, with me so far? That's just your regular 2-level model, even though it's technically level 3. Now let's put level 2 in there. And yes, I suspected that this might be a fatigue full time of day, so I'm helping. You get the Where's Waldo arrow for everything that's new in here. So I've picked up this U at level 2 here, and the change in the code then involves adding a random line. So I'm adding level 2. I'm testing whether or not occasions from the same day are more related such that they need an extra source of covariance that shows up via this level 2 random intercept. The line that's not here is repeated because we have unbalanced time, and so we're not doing anything with the R matrix yet, although I will show you how to do an AR1 for unbalanced time in a little bit. So this is my fit for the DV from a 3-level model, 2-level versus 3-level. Here's my likelihood ratio test from the fit test macro. -2 log likelihood difference is 75, so yes, occasions from the same day are more related than occasions from different days, even after controlling for which person it is. How related are they? Let's carve it up. So my person variance is just about the same as before. It's 6. But what used to be about a 6 for residual has been split into what is still residual, which is the 4, and what is day, which is the 1. These 3 sources of variance are orthogonal, so I can sum them up to create 12. There should be an Excel spreadsheet that goes with this example in which I did all these calculations, by the way. So if we go just straight proportions first, and by the way, this is exactly what I'm going to ask you to do on your homework. I've already started building this in. Of the total variation, 51% is at level 3, which is persons. Some people are more tired than others, and that's 51% of the action. Of the total variation, 13% is at day. Hang on. Copy and paste error. This is person, this is day, and that's time. Sorry about that. I will fix this and post it again. There. I need them to be aligned. I can't handle it when they're not. There. There. Person, day, and time. 13% is across days, and 36% is across time within a day. So 36% is within day changes in fatigue, 13% has to do with which day it is, and 51% has to do with which person it is. So the 2 new interclass correlations, ICC level 3b, which expresses how much of the variation is level 3, is cross-sectional. That's the same thing as just taking the straight proportion. So when you get a level 3 interclass correlation out of theta or M+, that's the version it's giving you, just the straight proportion. It is the correlation of occasions from the same person, ignoring which day it is, essentially, lumping that all together. It's the proportion of variance that's cross-sectional. The level 2 one, then, is carving up 2 and 1. So of the total variance that is either 2 or 1, how much of it is 2? That's 27%. So the expected correlation of occasions from the same day is 0.27. 27% of what we were lumping together as within person is actually day-specific. And the fact that our significance test for a 3-level model in searching level 2 was significant tells us that that 27% is greater than 0. Okay, how are we doing? So if I want to predict variance in fatigue, what kind of predictors are my best bet? People things, day things, or occasion things? People things, yeah. Followed by occasion things, followed by day things. But there's all three. Last night's sleep, I need to carve that up. Last night's sleep is a level 2 predictor. So the most it needs is 2 levels of variance, not 3. So I did a model predicting last night's sleep, adding a random intercept for persons to see how much of the variance in last night's sleep is person level versus within person. The interclass correlation for it, just a level 2 interclass correlation. I guess it's technically 3 since you're talking about person, it's 3, but whatever. 27% of the variation in last night's sleep is specific to people. Some people sleep more than others. That's 27%. Sometimes, some days, one sleeps more than usual. That's the rest. So this result being not 0 and not 1 tells us that last night's sleep is not just a sleep day level thing, it's also a person level thing. If there was no commonality in how much people slept, if some people did not sleep more than others, what would this number be? Got one, it's 1 or 0, we got votes. If there was no commonality across people in how much they slept, that's the 0. That would mean that last night's sleep is purely level 2 information and you wouldn't have to worry about the person variance in it. And if people slept the exact same every single night, then it would be 1. And you wouldn't have to worry about the level 2 variation in it. So somewhere between 0 and 1 for a level 2 predictor means it has some potential for a level 2 effect and some potential for level 3. Here's negative affect. I went through the same sequence of empty models as for fatigue, fitting just between versus within person, level 1 and 3. And that interclass correlation was fairly high, 0.77. So some people are grumpier than others, and that's 77% of the variance. Shocking, I know. Inserting a level 2 random intercept for day into the middle, separating what we would lump together as just within person as within day and between day, created an interclass correlation for level 2B of 0.12. So 12% of what we were calling within person is actually day specific. So the proportions are given right here. 77% of the variance in negative affect is person level, even though it was measured 4 times a day for up to 20 days. 77% of it is constant to the person, common to the person. About 3% is common to the day within a person, and the remainder is fluctuating across the day in some capacity, changing or fluctuating. And now day. We're using time of day as a predictor, so I need to do the same thing. So I'm treating it the same way as fatigue and negative affect, between person versus within person first, and only 2% of its variance is person level. So 2% of what time they took the survey is constant to the person, meaning there's a little bit of variance because some people took their surveys later or earlier than other people on average. There's a little potential for a contextual effect there, so I'm going to worry about that. It is significant, though. Here's my likelihood ratio test for that 2%. And here's what I got when I looked to see if people took their surveys later on some days than others. Pile of dots, meaning it couldn't find a day-level intercept variance. If it couldn't find it, you can't keep that model. And given the design of the study, in which they tried to keep survey administration time constant across days, this means that they did a good job of trying to make that work. So most of the information about time of day is level 1, as we would expect. A little bit of it's at level 3. Some people took their surveys on average later than other people. Okay. How are we doing? So what we've done at this point then is take every variable we're interested in and subject it to empty models to see where its variance lies. Fatigue is our outcome. It has variance that is within days, which was, let me get the numbers here, 36%. It has variance that is between days, 13%, and it has variance that's between persons. Likewise, negative affect, let's see, where did that go? Here it is 77% between person, 3% between days, and 20% within days. And sleep, which is level 2, is 77% between person, with the remainder within persons across days. And last but not least, time of day is mostly level 1 with a little bit at level 3. So that's piles of variance, and which predictors have which piles at what level. Next step is talking about time. So in intensive longitudinal studies, and this is the paper that I want to write, no one take my idea who's listening at home. I have seen otherwise well-intentioned people throw in time, and you're done, right? Just throw in a linear slope for time, F it, we're done, I controlled for time. Now, in this study where people are not being treated or otherwise manipulated, they're just filling out their surveys every day, do you think that fatigue would have a linear slope across time? That you just keep getting more and more and more and more tired as the day goes on? Or more and more and more tired as the study goes on? Or less and less and less and less? Does a linear slope for time make any kind of sense here? No. But what does it make sense? Well, I might have some intuitions. I know I'm tired in the morning, and I get really tired around like 6:30 at night, and I want to go to bed. And by the time I actually go to bed, I'm sort of back awake again, right? I know my own rhythms. You know your own rhythms. But what fits these kids? I'm not a teenager anymore. I have no idea what the kids do. I know they don't match their socks. They don't speak in complete sentences. They dye their hair weird colors. That's what I know about children. So let's make some pictures. So I'm going to look at time by fitting saturated means models for different types of time. So saturated means is when you let each occasion have its own mean. I'm not fitting unstructured variance like we would normally do because there's too much data to do that, so I'm keeping my level 2 and level 3 random intercept, and I'm throwing in rounded versions of time just to make pictures with. So I took time of day, I rounded it to the nearest half hour, and I threw that in a saturated means model. I'm using Glimix because Glimix will make me a plot. And here's my plot. I took that data and I threw it into Excel to make a trend line because I know how to do that in Excel, and I didn't want to look it up for SAS, and this is what it looks like. So as you might expect, people are tired around 6 in the morning. They get less and less tired as the day goes on. So actually, you guys should be fine. Maybe just the teenagers, I don't know. But, or is it because like you've already been up since before 6? Maybe that's, but I digress. And they get more and more tired as the day goes on. So to me, this looks like a pretty textbook quadratic pattern. Quadratic gets a bad name because it predicts that what goes up must come down and vice versa. And so if you're applying it to a trend that doesn't change direction, it doesn't work, but this looks kind of quadratic-y. And so I centered time in the models that follow at hour 15, which is 3 p.m. here. So I'm going to be estimating one's change in fatigue sort of instantaneous to the middle of the afternoon. And I'm going to model this with a quadratic. I won't have a clear and easy way of testing whether quadratic is enough, but it certainly makes a good theoretical sense, and it looks like it. So I'm going to go quadratic time of day. Then we have day, right? We need to know, are there any trends in fatigue that have to do with what day it is? Well, here is day of study. And note the giant confidence windows around these things. Do you see a trend there? Anyone? Because I don't. I don't have any reason beyond initial study reactivity why fatigue would change across days in case unless they just really hate filling out the survey, but they're paid, so they can't hate it that much. So I see no trend here. I'm not going to worry about day and study. I would write a sentence that says, I looked at this and it's fine. However, remember that whole day of the week thing? Wait for it. You know what day 2 is, folks? Monday. Our sample has a case of the Mondays. Please tell me you get that reference, because I may have to get out the YouTube. Yeah, case of the Mondays, right here. Interestingly, Thursday. Thursday's a good day. They're less tired on Thursdays. But that wasn't significant. So given this trend, I'm not going to try to fit some sort of cubic trajectory here. I'm just going to stick in a dummy code for whether or not it's Monday. And LS means follow-ups across these days would support that. Day 2 is really the only one that was different. So I'm going to control for Monday. So I'm sticking in, as we'll look at next time, a level 2 variable for whether or not it's Monday. And so that's where we're going to head. So first up, we'll be getting a hold of all this time stuff. Then we can look at negative affect, and then we can look at sleep. But we will get to do that next time. So any questions on that thus far? All right. Then office hours start now. Let me know if you need anything. Otherwise, I hope to see you on Wednesday.